Well, while we're waiting for the slides to load, I want you all to know this has been an extraordinary experience for me as a weed scientist. I can tell you, as in my discipline, we tend to be quite siloed, and not only just getting to work with entomologists, pathologists, and soil scientists, but beyond that, the climate scientists have really helped me personally. Thinking more broadly about what the ultimate impacts of this project will be, particularly as it pertains to Objective 5, organismal biology research. I think a lot of it will be the forging of these collaborations that maybe we would not have ever had an opportunity to do as part of this process. So I know for me, learning about insects and diseases and earthworms wasn't necessarily very high priority on my list of things to do professionally, but I've certainly been profoundly improved as a scientist as a consequence of it. So the other big impact I think that our little team has had is that it turned into a big team and a very diverse team. And many of the people on this list that have worked with us, the principal scientists, including Sanford and Tim and Nilsa and Dave and Jody, but also the undergraduate students and the graduate students have moved on to some positive things. So Nevin's an assistant professor. Seth and Brad are both assistant professors. I know in my own undergraduate intern group, Laura's just completed an MS degree at the University of Illinois. Nick just applied to University of Wyoming, and Jonathan is in the Peace Corps. So the waves are spreading out from our program, I think, and I think each of us who have directed students have similar stories. So the Objective 5, the biotic team had some very simple objectives. We thought they're certainly easy to read, right? So we want to anticipate and develop approaches to climate-related changes and crop protection requirements due to pests, and also understand the effects of beneficial biota within our cropping systems. But the practical way to address those very simple questions became very profoundly difficult. I can remember sitting down in the very first few meetings with just Jody and Sanford and Tim and I going, so are we going to actually get in the same trucks and drive around the state at the same time? Can we even do that? No, you can't. The organisms we're sampling are so profoundly diverse, and they're all climate has very strong effects on each of them in different ways that it was a very, very much a positive learning experience, not only focusing on our own individual organisms, but understanding the interrelationship, the potential interactions that they have. So what we started with was this rather jumbled list of pathogens and insects and weeds and soil biota and individual research projects. Ultimately, mainly due to Sanford, evolved into something that looked more like a lot more rational image. And of all the things that we've been able to accomplish, this is probably one of the things I'm most proud of. So this is a temporal figure as well as a trophic level figure. And so we have a temporal nature of the figures captured in the growth of the crop that we're interested in studying, and then the associated climate inputs and management inputs that go into producing that crop, and the associated soil management. And then as a consequence of and interrelated to those efforts are all the pests and beneficial organisms that we studied in the Objective 5 effort. And they're arranged in their various trophic levels. For instance, we conducted research that examined how weed seed were predated by earthworms, as an example. So all of that is captured here, and what we hope to do moving forward, well, I'll get to that in a minute, is be able to manipulate and understand how our manipulations here at the bottom might affect the outcome at the trophic levels here at the top. That's not possible without integration with the other objectives, and so this is just a very brief list of some of the ways that we've been able to integrate and use the information generated by the other objectives in our own, including getting Claudio to attempt to incorporate modeling the response of of wheat to pests, and then also utilizing a whole host of environmental data, as I'm going to give you some very specific examples here in just a second. We also work to monitor many of the rotational systems that were put in place as part of Objective 3, and also contribute a lot of questions to Objective 4. So I can't say that it was necessarily always a two-way street, but we certainly got a lot from all the information that was being generated by other parts of the project. So I'll go through just a few specific examples because there's not enough time to go over all the things that the objective really accomplished. The first is some data generated by Dr. Politz. This is a network analysis of bacteria in relationship to Rhizoctonia bare patch. Rhizoctonia is a pretty bad disease of wheat. It causes rather large open spaces to appear in the field where the wheat just isn't as vigorous, and that's an entry point for weeds and a host of other problems. Tim's been very interested in understanding how to mitigate the duration of time that those patches are present. And we know that certain rotations can contribute to their diminishment, but he's also been trying to understand how the different bacterial associations might potentially impact. And what he's discovered is that there are associations of bacteria found in the bare patches and in affected wheat where the wheat is just not growing, and then there's a very different group of bacteria associated with more healthy plants. So it's potentially a weaponizable bit of information to minimize those bare patches, the duration of those bare patches. Jody's been working to understand climate effects on earthworms, and this was really her opportunity to do it on a regional basis. And she learned that there's a very specific period of time during the season where earthworms are really the most active, and it's not most of the year. It's a very limited period of time in the early season. So you can see the soil temperatures here on the vertical axis, and on the horizontal axis is our Julian calendar. And most of the earthworms are not active. Earthworms are not active when there isn't sufficient soil moisture. They're estivated. So if the ground's frozen, they're not active. And if the soil is too dry, it's not active. They're not active. They're estivated. So there's a very brief period of time where they're active and moving things around. This is very beneficial information for helping growers potentially culture their own earthworm populations. The other thing she discovered was that there's just not earthworms in the low precipitation areas. So you can see the annual precipitation on the vertical axis, the number of individuals on a meter square basis, and annual precipitation on the horizontal axis, and anywhere below about 11, 12 inches, there's not earthworms. And that's useful information for understanding how climate might affect earthworm populations moving into the future, potentially help us predict them. For weeds, we've really focused on downy brome within my own project, and this is just an example of how we reached out to our climate scientist, John Abotskloo helped us model how downy brome life cycles might change in the future. And using multiple assemblages of models, we can predict that downy brome could flower as much as 20 to 25 days earlier than it currently does now in the 2050, 2060 timeframe. That's a significant advancement in its life cycle potentially, and it's something that really sort of caught us by surprise because many of our growers are cued to make herbicide applications for managing downy brome on the basis of wheat growth, not downy brome growth. And so as I kind of walk through the worst case scenario is advancing 28 days. If nothing really changes, we can at least see some potential advancement by 5 days on average. So all of that put together really helped us build a perspective on how our producers are managing not only downy brome but other weeds. So this is sort of this is what the current situation is, where growers use a wheat growth stage to go out and assess their population, or assess their crop growth, and they make a decision on whether or not to apply based on a host of other things, not just weeds. But what we're realizing now is that for this particular pest, that's actually a very counter to actually managing it. And so we're going to begin, moving forward, we're working on, instead of using a wheat model for advising when to manage downy brome, we're going to begin to not only advise them on the basis of downy brome growth, but also start to build in seed dormancy and vernalization traits that we can actually test on individual growers' fields. We want to be able to weaponize our basic biology information and help growers manage these damaging pests. And just to finish up, I have a couple of slides that Sanford was willing to provide. This is Sanford's interested in understanding aphids. He went out and his staff and students sampled multiple times throughout the growing region, and very quickly realized that they had a new species of aphid that they were dealing with. And not only was it a new species, it was one of the most common found at multiple sites throughout the region. So he and his staff and research crew spent a fair amount of time trying to understand what the implications of that, because it was an unknown pest. It had only been previously found, I think, in one other state in the United States, and it really wasn't associated with wheat that we thought, but here it is, one of the most common aphid species found. And that's sort of indicated by this darker pink circles, or lighter pink circles. That's the species that was the most common at many of these sampling sites. Thankfully, it was found to not transmit common diseases like barley yellow dwarf, which was a positive, but it certainly seemed to be quite damaging to the wheat itself. The other thing that Sanford was interested in studying was cereal leaf beetle, and this was sort of science that really began to elevate our thinking about these trophic levels and the impacts of climate, how the impacts of climate would change the relationships among these species. This is an excellent example of that, where it's parasitoid and cereal leaf beetle, their activity periods might be diverging, so that the biocontrol might not be up and functioning at the same time that cereal leaf beetle is moving into the future, so that the percent of parasitism might actually decrease with changes in climate. And in cereal leaf beetle actually might become a little bit more damaging to a lot more damaging across the region as well. So a very good example of how these pests are interacting. So future work for our team, I fully anticipate continuing to interact as a group, but to begin to more fully develop a way to address all of the interactions that you see on this chart, more fully to understand those sort of very complex trophic level, climate level interactions among both our crops and our pests and beneficial organisms. And I'll finish up with just a list of impacts. Of course, there's associated publications with each one of those that are on the list, and this was just the ones that we had time to get submitted into our final review document. There are a lot of other excellent examples of research projects that have come out of our objective. So with that, I'd be looking forward to your questions in the panel.